Lithium-ion is everywhere around us. In phones, laptops, and more than 95% of today's EVs still rely entirely on this technology. That number alone is enough to show that lithium-ion remains the gold standard in the battery world, with few competitors capable of replacing it. But the truth is, lithium-ion batteries have been standing still for the past few years. How long has it been since we saw a real leap in performance? Energy density is still stuck at around 250 watt-hours per kilogram. Prices haven't dropped significantly, and the risk of fire or explosion remains a constant concern. This is also why electric vehicles still haven't convinced all consumers. They remain expensive, and safety concerns continue to linger. Recently, EV manufacturers have begun shifting to a newer option, one considered far more efficient than lithium-ion's aging limitations: solid-state batteries. Solid-state batteries aren't just hype, backed by rapid R&D and billions in investment from giants like BYD, Tesla, Toyota, and QuantumScape. This next-gen tech is already outperforming lithium-ion in energy density, range, and charging speed. Mass production could start as soon as 2026. Could this be the final catalyst for EVs to leave gasoline behind for good? And what sets an EV with solid-state batteries apart? Welcome to Tesla Car World. So, what makes solid-state batteries worth paying attention to? We all know that most new battery technologies still haven't earned the public's full trust, and for good reason. Many are still stuck in the research or testing phase, and bold claims about breakthrough performance often come without real-world proof. But in the middle of all that noise, BYD, one of the world's leading EV and battery tech companies, and a top rival to Elon Musk's Tesla, is making some serious waves. As you may know, BYD is already behind the Blade battery, a lithium iron phosphate battery known for its safety and durability. So reliable, in fact, that Tesla uses it in its Model Y sold in Europe. But now BYD is going even further by developing the very battery the world has been chasing: solid state. They've already built a working prototype on a pilot production line, and are expected to begin large-scale installation in their vehicles soon. This new battery boasts double the energy density of current cells, enabling up to 900 miles of range on a single charge. And that charge takes just over 4 minutes. If BYD sticks to its roadmap and delivers as promised, this battery could completely reshape the global EV market within this decade. Solid-state batteries mark a major leap forward in energy storage technology, by completely eliminating flammable organic solvents and replacing them with solid materials like ceramics, sulfides, or polymers. This shift allows energy density to reach 400 to 500 watt-hour per kilogram, 2 to 3 times higher than that of traditional lithium-ion batteries. Imagine a suitcase the same size, but now able to hold twice as many clothes. Thermal resistance also sees a huge boost. Solid-state batteries remain stable across a wide temperature range, from -4 degrees Fahrenheit to 212 degrees Fahrenheit, equivalent to -20 degrees Celsius to 100 degrees Celsius, drastically reducing the risk of failure due to extreme heat or cold. Durability? Even more impressive. With no more electrode wear or swelling issues, solid-state batteries can handle 2,000 to 3,000 charge cycles, while still retaining over 80% of their performance. That's like doubling the driving distance of a car before it ever needs a major overhaul. It might sound almost too good to be true, but these very advantages are exactly why battery giants around the world are racing towards solid-state technology. In addition, many leading corporations are actively developing and commercializing solid-state battery technology. QuantumScape recently reported a breakthrough in its Cobra project, the successful fabrication of a micrometer-thin ceramic separator, a crucial step, as thinner separators lower interfacial resistance and enable higher current density. This new production method is said to be 25 times more efficient than the previous Raptor generation. The company has also partnered with Volkswagen's PowerCo, targeting a commercialization window between 2026 and 2028, in sync with the rollout of next-gen EV platforms. Solid Power, meanwhile, is focused on sulfide electrolytes, reporting room temperature ionic conductivity of approximately 1 millisiemens per centimeter. While not the theoretical maximum for sulfide systems, it's strong validation of their cell architecture, proven through 1,000 cycle tests on the BMW iX, a notable real-world milestone. On the oxide front, Toyota is developing LLZO, lithium lanthanum zirconium oxide, a solid electrolyte with a high melting point and stable performance from -4 degrees Fahrenheit to 212 degrees Fahrenheit. Their plan to integrate it into Lexus EVs by 2027 shows strong confidence in both its thermal and mechanical durability. As for manufacturing capacity, Ferasis Energy has launched a 0.2 gigawatt-hour pilot sulfide battery line in Germany, aiming to scale up to 1 gigawatt-hour per year by 2026 for both EVs and grid storage. Finally, Huawei has unveiled a hybrid sulfide polymer battery boasting 450 watt-hour per kilogram energy density, over 2,000 kilometers of range, and an 80% charge in just 10 minutes. Impressive figures that, while promising, will need to be validated through rigorous life cycle testing and the demanding conditions of the automotive industry. The truth is, every time a new battery type makes headlines, most people probably just roll their eyes and think, "Oh great, another gimmick." There's a common belief that these new batteries will never make it to mass production, let alone become mainstream in electric vehicles. And, honestly, we used to think the same. That reaction is completely understandable. Lithium-ion has earned its place as the gold standard for EVs thanks to its stable energy density and a dramatic drop in cost. From around $1,000 per kilowatt-hour in 2010 to roughly $130 per kilowatt-hour by 2024. However, take a closer look, and it's not just us. Many experts agree. Lithium-ion is one of the biggest reasons EV performance has hit a ceiling. Despite being widely adopted for decades, this technology has slowed innovation and eroded public confidence in electric vehicles. By key metrics, traditional lithium-ion batteries typically offer around 180 to 250 watt-hour per kilogram. In contrast, next-gen solid-state designs are targeting 400 to 500 watt-hour per kilogram. That kind of jump can translate to either lighter battery packs or significantly longer driving ranges, without increasing size or weight. Lifespan also tends to favor solid-state batteries, instead of the typical 1,000 to 1,500 full charge. Discharge cycles seen in lithium-ion batteries, solid-state batteries can deliver around 2,000 to 3,000 cycles, meaning their capacity fades more slowly over time. Charging speed is another key differentiator. Most lithium-ion battery systems go from 0 to 80% in about 25 to 35 minutes, while solid-state tech is targeting just 10 to 15 minutes, significantly cutting downtime. They also operate within a much broader temperature range, from -10 degrees Celsius to 50 degrees Celsius for lithium-ion, compared to from -20 degrees Celsius to 100 degrees Celsius for solid-state, which could simplify thermal management systems. Safety rounds out the list of advantages. By replacing flammable liquid electrolytes with solid materials, the risk of thermal runaway drops from moderate to high to virtually zero. That said, current lithium-ion chemistry still holds key strengths. It's proven, mass-produced, and highly cost-optimized. Top-tier lithium-ion cells are already pushing the upper limits of their energy density range, though results vary based on cell format and pack design. Some of the most impressive solid-state metrics come from controlled prototypes and transitioning those into mass production, while maintaining fast charge durability and addressing interfacial resistance, remains an active engineering challenge. For now, lithium-ion remains the practical choice for mainstream applications, especially where cost and supply chain maturity are critical. Still, the direction is clear. If manufacturers can industrialize solid-state batteries without compromising these numbers, they offer a compelling foundation for the next generation of electrified systems, with higher energy, faster charging, greater thermal resilience, and improved safety. When will semi-solid batteries hit the road in EVs? Lithium-ion batteries have long struggled with key challenges, including the risk of fire or explosion due to thermal runaway when damaged or overheated. On top of that, technological progress has been relatively slow, with energy density improving by just 5 to 10% per decade. Environmental concerns are also mounting, especially around the mining of raw materials like nickel and cobalt. Solid-state batteries offer major advantages, up to 2 to 3 times the energy density of today's LFP cells, along with impressive durability and superior safety. They're almost non-flammable. This is exactly why the EV industry often refers to them as the holy grail of electric vehicle batteries. Put simply, every battery cell is made up of 4 key components: a cathode, anode, electrolyte, and separator. As the name suggests, solid-state batteries replace these components, most importantly, the electrolyte, with solid materials. What truly sets them apart is the solid electrolyte layer positioned between the anode and cathode, whereas traditional lithium-ion batteries use a liquid electrolyte in that same space. This is where solid-state batteries shine. They can store more energy, deliver higher power output, and are significantly safer than their lithium-ion counterparts. Liquid electrolytes in conventional batteries are flammable, prone to leakage if the cell is cracked, and can trigger thermal runaway, a dangerous chain reaction that spreads from one cell to another. In contrast, most solid-state batteries today use ceramics or polymers as solid electrolytes. The application roadmap for solid-state batteries kicks off around 2025 and 2026, focusing on validating the technology under real-world conditions. Prototype cells are already being tested in trial vehicles by BMW, Volkswagen, and Toyota, while pilot production lines are up and running in the US, Solid Power, Germany, Ferasis, and China, Huawei. The current priority is stabilizing manufacturing processes, controlling key variables like separator thickness and moisture levels, especially for sulfide-based systems, standardizing cell formats, and conducting safety evaluations at the module and pack levels, all essential steps toward meeting regulatory certification standards. From 2026 to 2028, solid-state batteries are expected to enter a limited-scale semi-commercial phase, with a focus on premium segments and industrial storage, markets that can absorb higher costs in exchange for better energy density and safety. As cumulative production approaches 1 gigawatt-hour, prices are expected to begin stabilizing. Manufacturers will concentrate on increasing production yield, reducing defects, optimizing thermal propagation control, and fine-tuning battery management systems for lithium metal anodes using real-world performance data. Between 2028 and 2030, the goal is to scale up to mainstream vehicle segments, particularly compact sedans and crossovers, comparable to the Tesla Model 3 category, as solid-state battery costs approach parity with lithium-ion battery cells. At this stage, they must meet demanding requirements: long cycle life warranties, minimal degradation under repeated fast charging, and full compatibility with 800-volt vehicle architectures. After 2030, the technology is expected to see widespread adoption across entire EV lineups and grid storage systems. This phase will go hand in hand with supply chain standardization, multi-source material strategies, the development of recycling protocols, and end-to-end cost optimization, all critical to ensuring large-scale reliability and sustainability. Back to BYD. The company has confirmed that its solid-state batteries deliver an energy density of 400 watt-hour per kilogram, nearly double that of conventional lithium-ion cells, which average around 210 watt-hour per kilogram, and significantly higher than BYD's current Blade battery, which offers about 160 to 165 watt-hour per kilogram. To achieve this performance, BYD has upgraded both the electrode materials and solid electrolyte. Reports indicate they use a synthesized oxide solid electrolyte combined with high-capacity anode and cathode materials to accelerate both charging and discharging speeds. These advancements also enhance ionic and electronic conductivity, boosting both energy density and overall battery efficiency. Imagine this. If you bought a current BYD Seal equipped with an 80 kilowatt-hour blade battery, you'd get around 373 miles of range. Now, with the new solid-state battery of the same size, that range could jump to an astonishing 870 miles. But here's the thing. You might not even need that much capacity. A smaller 60 kilowatt-hour pack could still deliver up to 621 miles of range. That's insane. The higher energy density of solid-state batteries means you can store more power without adding weight, a critical advantage for electric vehicles. Of course, 400 watt-hours per kilogram isn't record-breaking compared to some other solid-state contenders. Companies like Cattle, Amprius Technologies, and QuantumScape have already developed batteries exceeding 500 watt-hour per kilogram. But BYD is taking a more measured approach with its first-generation solid-state cells. Rather than chasing extreme specs too soon, they're aiming for a more attainable target, one that enables faster mass production and real-world rollout. From there, they can scale and improve. Why aren't solid-state batteries used in EV right now? One of the most critical barriers is the scalable production of ultra-thin ceramic separators. These separators, placed between the battery's anode and cathode, are crucial for the flow of ions. Unlike the flexible polymer separators used in lithium-ion batteries, ceramic separators are rigid and fragile, making them prone to cracking during large-scale manufacturing. Producing them at commercial volumes with micron-level precision and mechanical durability has proven difficult. Many pilot production lines still suffer from high defect rates and unstable yields. Without a breakthrough in processing techniques and quality control, this component alone threatens to slow the rollout of solid-state cells. Another major obstacle is performance at low temperatures. Certain sulfide-based electrolytes, widely considered among the most promising candidates for solid-state designs, tend to lose significant ionic conductivity below 0 degrees Celsius. This degradation severely limits their functionality in colder climates, such as Europe, Canada, and the northern United States. For solid-state batteries to succeed globally, they must perform reliably in winter conditions. Achieving this will require new formulations or hybrid solutions that maintain conductivity without compromising stability or cost. Without progress here, many high-value markets will remain out of reach. Which solid electrolyte chemistry do you believe holds the most promise for commercial EV applications, and why? Please share your opinion in the comments section below this video. Thanks for watching our video. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Also, make sure to subscribe to Tesla Car World and turn on notifications so you never miss our latest videos. The EV market is seeing a surge of automakers popping up from China to North America, and the pressure's on for manufacturers to innovate. They're being pushed to develop breakthroughs in battery tech that are at least cost-effective, energy-efficient, and safe. In this race, whoever comes up with the better battery will come out on top. In the long run, Tesla can't keep relying on lithium-ion batteries. Those just won't cut it for making Elon Musk's EVs cheaper and more accessible to consumers, since Tesla's cars are still pretty pricey. So what happens if Tesla develops a battery that's 3 times cheaper than lithium-ion, charges twice as fast, and is 100 times safer? Sounds hard to believe, but it's getting closer to reality. We believe there are 3 reasons why these batteries are game changers, some of which are so impressive that we find ourselves thinking we're witnessing a historic turning point no one saw coming. No one expected sodium batteries to be this good, and even fewer imagined they could power a vehicle for over 4 million kilometers. Actually 4.8 million kilometers, which is nearly 3 million miles. As usual, sodium-ion batteries might be a familiar concept to energy tech enthusiasts, but most people still don't really know what they are, aside from assuming they contain sodium. That's not wrong, but we believe the concept of sodium-ion batteries is far more fascinating than that. Simply put, a sodium-ion battery is basically made up of a cathode, made from materials capable of storing sodium, an anode, typically made from hard carbon, alloys, or metal oxides, and a liquid electrolyte containing sodium atoms in ionic form. The electrolyte is the liquid between the 2 electrodes filling the inside of the battery cell, and acts as a bridge that allows sodium ions to move between the cathode and anode. Switching from using a lot of lithium to more sodium mainly changes things like energy density, charging time, safety characteristics, and overall performance metrics. But it doesn't change the basic working principle. In fact, the operating principle of sodium-ion batteries is the same as that of lithium-ion batteries. Many of the electrode materials used in sodium-ion technology are actually borrowed from lithium-ion battery designs. Sodium ions move from the cathode to the anode during charging, and back from the anode to the cathode during discharging. Hopefully that gives you a clearer understanding. Now let's go back to the original question. Why would Tesla use sodium-ion batteries, and why has Tesla been slow to adopt them? Let's tackle the positive side first. Why Tesla will use sodium-ion batteries? Tesla adopting sodium-ion batteries doesn't mean they'll stop using other types of lithium-ion batteries. Each battery technology has its own strengths, which makes it better suited for different Tesla vehicle models. Have you ever wondered why we should even consider switching to sodium-ion batteries when lithium-ion has long been seen as the gold standard? The answer is pretty straightforward. Lithium-ion batteries can't solve many of the challenges that EVs are currently facing, especially as more automakers aim to produce more affordable EVs. That's right. One of the main reasons sodium-ion batteries are being developed is because sodium is far more abundant and significantly cheaper than lithium. This becomes especially important as demand for battery-grade lithium continues to surge, with forecasts predicting a lithium shortage for lithium-ion battery production by as early as 2025. Sodium-ion batteries offer a particular advantage for all automakers, but especially for Tesla and its long-rumored $25,000 EV, thanks to their lower cost. Adding a new battery chemistry that doesn't rely on lithium into the supply chain could bring massive benefits, especially in a future where lithium demand could increase 500 times over today's levels. Experts like Tony Seba have even predicted that EV prices could drop as low as $5,000 with these ultra-low-cost batteries. According to Energy Post, the production cost of sodium-ion batteries could eventually drop to around $40 per kilowatt-hour, which would make it one of the lowest-cost battery technologies available. Tesla's biggest partner, CATL, is currently producing sodium-ion battery cells at around $70 per kilowatt-hour, but the company has promised that this could drop below $40 in the future. As the world's leading battery manufacturer, CATL has made a major breakthrough in its production process. It's easy to see the pricing potential of sodium-ion batteries, especially considering that even the cheapest lithium iron phosphate battery cells on the market today still cost about $90 per kilowatt-hour. While lithium naturally exists in various types of rock and some brines, the amount of lithium in Earth's crust is not unlimited. In addition, lithium extraction is energy-intensive. The high demand for this raw material, combined with its limited natural supply, has driven prices up significantly, earning lithium the nickname white gold. By contrast, sodium makes up about 2.6% of Earth's crust, making it highly abundant and much easier to extract than lithium. On top of that, the cathode materials used in sodium-ion batteries are typically made from iron and manganese, instead of nickel or cobalt, which are used in many lithium-ion batteries. Both iron and manganese are widely available around the world and are not considered at risk of depletion. So, how fast can sodium-ion batteries charge? For those frustrated with long charging times, EVs still raise concerns, especially on trips longer than 400 miles. In Tesla's current lineup, the fastest charging time is about 35 minutes to go from 20% to 80%, as seen in the Model 3 equipped with an LFP battery pack. If Tesla wants to shorten charging times, sodium-ion batteries might not be the ultimate solution, at least not yet, even though some battery technologies have already achieved impressive charging speeds. Still, compared to today's standards, sodium-ion batteries are definitely more efficient than lithium-ion in terms of charging. Specifically, sodium-ion batteries have the potential to charge faster than lithium-ion batteries. CATL has claimed that their sodium-ion batteries can reach 80% charge in just 10 to 20 minutes, which is noticeably faster than Tesla's current EVs that typically take about 30 minutes to hit the same level. What's even more impressive is a new breakthrough in battery tech that shows just how insanely fast sodium-ion batteries could eventually charge. If you search for the phrase sodium-ion battery charging time, You'll find reports of researchers developing a new sodium-ion battery that can charge in just a few seconds, thanks to a high-performance cathode with characteristics similar to a supercapacitor. This is a massive leap compared to current lithium-ion batteries, which can take nearly an hour to fully charge. Why does Tesla need the safety advantage of sodium-ion batteries? Right now, a common perception still lingers that EVs are like ticking time bombs, potentially prone to exploding after 4 to 5 years of use. And when an EV catches fire, it's extremely difficult to estimate how much water is needed to extinguish the lithium battery packs. That concern isn't unfounded. We won't deny that lithium batteries can be dangerous, but to be fair, these incidents are extremely rare, with an incredibly low failure rate. Still, that's with lithium. The story is entirely different when it comes to sodium-ion batteries. Sodium-ion batteries ensure high safety standards, as battery cells based on this chemical element are non-flammable, non-explosive, and have a low risk of short circuits, meaning sodium is virtually incombustible. CATL has proven this through tests such as multi-directional compression, nail penetration, electric drilling, and even being set on fire, without catching fire or exploding. We've never seen a lithium battery withstand these kinds of tests. Most will either explode or ignite almost instantly under such conditions. On top of that, sodium-based batteries can endure extreme temperatures, operating reliably in a wide range from -20 degrees Celsius to 60 degrees Celsius. In contrast, lithium-ion batteries typically perform best only within a narrower range of 0 degrees Celsius to 50 degrees Celsius. More specifically, sodium-ion batteries show better performance at low temperatures, maintaining over 92% of their capacity at -20 degrees Celsius. In a press release from CATL about their sodium-ion technology, they confirmed similar claims regarding cold weather performance. In lab tests at -30 degrees Celsius, the battery was able to charge from 30% to 80% in just 30 minutes, while still retaining 93% usable capacity. Even with only 10% charge remaining, EVs using these batteries could still drive on highway speeds at 75 miles per hour. Beyond cold weather performance, safety is another major advantage. Sodium-ion batteries are generally considered safer than lithium-ion because sodium is less reactive than lithium. There's also another benefit that anyone can appreciate: lower toxicity. Sodium-ion batteries don't require lithium, cobalt, or nickel, metals that can release toxic gases when burning, and they're also more adaptable to a variety of use cases. Finally, sodium-ion battery-powered EVs could appeal to urban and suburban users on a tight budget, people who don't really need a car for long-distance travel. So, how long do sodium-ion batteries last? That's the focus of today's episode, and also the biggest advantage of sodium-ion batteries. For energy storage applications, improving cycle life is essential. And when it comes to EVs, battery lifespan is even more important. EV batteries aren't cheap, and none of us want to be replacing our car battery after just 2 or 3 years. According to publicly released information about CATL's sodium-ion batteries, their lifespan is relatively long, projected to reach up to 10,000 charge cycles, which equals about 4.8 million kilometers, nearly 5 million. An absolutely impressive number compared to current commercial lithium iron phosphate batteries, which typically last between 2,000 and 3,000 cycles. 10,000 cycles means the battery pack could last up to 20 years if properly maintained. Oh my God, this is definitely great news for anyone worried about the cost of replacing an EV battery. CATL has been fairly cautious with their battery lifespan projections. They're not making exaggerated claims without real-world results to back them up. So, with the 3 main reasons mentioned above, it's easy to see why more and more companies are developing sodium-ion batteries. Thanks to these standout advantages, this technology has real potential to convince Elon Musk to consider using it in Tesla, especially for compact, low-cost cars in the future. However, there may still be 1 or even 2 barriers that make Elon Musk hesitant to adopt this battery technology. So why has sodium-ion battery technology been slower to arrive Tesla? Even though sodium-ion batteries offer strong performance, they're still relatively new to the commercial market. Widespread use of this energy storage type remains limited due to the lack of a stable industrial supply chain. One major limitation of sodium-ion batteries is energy density, the amount of energy stored per unit of battery weight. Currently, sodium-ion batteries have a relatively low energy density, ranging from 140 watt-hours per kilogram to 160 watt-hours per kilogram, whereas lithium-ion batteries today typically range from 180 watt-hours per kilogram to 250 watt-hours per kilogram. A battery's energy density is a critical factor that affects its efficiency and range of applications. High-energy density batteries can deliver large amounts of power in a compact size, which is especially ideal for EVs. With the same physical size, a high-density battery provides longer usage time compared to a low-density one. Additionally, high-density batteries are often lighter, helping to reduce the overall weight of a device. In contrast, low-density batteries usually need to be larger to deliver the same amount of energy, which can result in shorter usage time. And to achieve the same capacity, a lower-density battery will also weigh more. This is the exact challenge that sodium-ion batteries are facing, and one of the main reasons why this technology has developed more slowly than the rapid advances in lithium-ion battery technology. However, there's still plenty of hope, as CATL is expected to launch its second-generation sodium-ion battery soon. CATL has announced a target of reaching 200 watt-hours per kilogram for its next-generation version, currently in development, compared to just 160 watt-hours per kilogram for the current generation. What's more, as we mentioned earlier regarding sodium-ion battery technology, a former Tesla engineer has founded his own company focused exclusively on developing this type of battery. He's confident that his sodium-ion battery can achieve a driving range of up to 300 miles, which is the most ambitious claim we've heard so far about sodium-ion batteries. The main reason sodium-ion batteries have lower energy density is because lithium ions are smaller and lighter than sodium ions. This smaller size allows lithium ions to pack more tightly into electrode materials, enabling more energy to be stored per unit of volume or weight. Additionally, lithium has a lower electrochemical potential than sodium, meaning it releases more energy per electron exchanged during reactions compared to sodium. To reach higher energy density, CATL is addressing previous material limitations. The anode now uses Prussian white, which has been restructured at the electron distribution level to solve the issue of performance degradation over many charge cycles. The cathode, according to the company, is made of hard carbon with a porous structure that allows it to store more sodium ions and enable faster ion movement. CATL says their sodium-ion battery could be commercially viable if these material improvements deliver the expected results. Well, we'll have to wait and see what the next stages of development bring. Over the past 20 years, more than 50% of sodium-ion battery research activities leading to patents have taken place in China, 53%, followed by Japan, 16%, and the United States, 13%. Europe is also beginning to make progress in this field. According to forecasts, the sodium-ion battery market is expected to grow at an annual rate of 27% over the next decade. Annual production could increase to about 70 gigawatt-hours by 2033, representing a nearly 600% growth. Sodium-ion battery technology could become more widespread in the future, thanks to the fact that many manufacturing processes for sodium-ion and lithium-ion batteries are similar. This similarity facilitates easier conversion of production lines and can even reduce investment costs. To overcome the weaknesses of sodium-ion batteries, CATL has introduced an innovative idea: developing a hybrid battery. This solution involves mixing and combining sodium-ion and lithium-ion batteries in certain ratios, integrating them into a single battery system, and using an intelligent battery management system to control the different battery components. Depending on the requirements, a vehicle can leverage the sodium-ion battery's performance in low temperatures or the high energy density of the lithium-ion battery. The project is still in the testing phase, but the entire industry is closely watching this initiative from the Chinese company. Although challenges remain, interest in sodium-ion batteries is increasing in the electrification world. Major international battery manufacturers are gradually shifting their focus to this technology. CATL identified sodium-ion battery chemistry as a strategic target in 2021, presenting it as a new frontier for investment aimed at differentiating their products. The Chinese giant pursues this strategy based on the understanding that capturing part of the market currently dominated by lithium-ion batteries with sodium-ion alternatives could help drive lithium battery prices down significantly. Currently, Sodium-ion batteries are primarily used in small-scale applications manufactured in China, and we do not expect to see this technology in Tesla models anytime soon. While it may happen in the future, we believe it won't become a reality until CATL successfully commercializes its second-generation sodium-ion batteries, with energy density high enough for Tesla to consider adopting them. However, the EV industry is not just Tesla. Many other automakers are struggling with advances in battery technology, and sodium-ion batteries could be an effective option for them. Additionally, sodium-ion batteries could see wider use in the future for stationary energy storage applications. As Tesla aims to make its EVs more affordable and accessible to a broader audience, sodium-ion batteries could be a suitable choice because they offer three core benefits: low cost, fast charging, and high safety. And if sodium-ion batteries can overcome the energy density barrier, there's no doubt that mass production at Tesla's Nevada Gigafactory will soon become a reality. When considering the pros and cons of sodium-ion and lithium-ion batteries, it's clear that each type has its own strengths. Choosing between the two depends on specific requirements as well as considerations of cost and environmental impact. In the debate between sodium-ion and lithium-ion batteries, sodium-ion emerges as a promising alternative with advantages in cost efficiency, environmental friendliness, and safety. However, lithium-ion batteries still hold a dominant position due to their high energy density, well-developed infrastructure ecosystem, and technological maturity. In summary, the competition between sodium-ion and lithium-ion batteries reflects a positive shift toward more sustainable and efficient energy storage solutions. The battery technology landscape is constantly evolving, and the coexistence of these two technologies provides a diverse approach to meet the world's growing energy needs. Finally, what are your expectations for sodium-ion batteries? And what do you think if Tesla were to produce EVs powered by sodium-ion batteries? Drop a comment below. We truly appreciate your valuable feedback.
And then one other thing, we have a new HV battery. Now this battery brings in our latest and greatest in terms of technology. It is cheaper to manufacture. And the best part is that it's actually less battery energy than in our current pilot production vehicles, but it maintains the same range. This is achieved through efficiency improvements that we're showing here, more than 7% at this point.
This completely rewrites the rules of the market with the old belief that over time, you inevitably have to replace your car battery is no longer true. Here, everything improves automatically. If a Tesla battery can last 100 years, deliver a full discharge in just 42 seconds, and even perform better over time, still retaining around 80 to 85% of its original capacity after 10 years, then the game has changed. Sounds too good to be true, like something out of pure imagination? It does, but look closely. Tension is already spreading among the giants of the battery industry. China has just taken the hardest hit it has ever faced, the $340 billion monopoly it built around lithium is collapsing at breakneck speed. What was once seen as a strategic advantage has now become a glaring weakness. And in less than 3 months, more than 47,086 cyber attacks have been launched against Tesla's Gigafactory in Nevada, with one goal: to steal the secrets behind the new aluminum-ion battery production. So why are aluminum-ion batteries superior to lithium-ion? And can they shatter the current lithium-ion monopoly? Welcome to Tesla Car World. Take a look inside a lithium-ion battery. It's not exactly high-tech, just 2 meters of metal foil coated with a black adhesive, packed into a small cylinder weighing only 45 grams. Yet this simple construction powers everything from laptops and electric cars to satellites orbiting in space, serving both civilian and military purposes. The problem is, when a battery fails, all that stored energy can be unleashed in the worst possible way, leading to instant explosions with consequences that are almost unimaginable. So why is something so crude found in nearly every electronic device on the planet? And why don't we have something better? This is no coincidence, it's desperation. The relentless pace of improvement poses a direct threat to business models built on planned obsolescence, a practice that has long been the norm in the auto industry. Manufacturers have relied on battery wear and tear to drive profits from scheduled replacements and costly maintenance. But now that strategy is at risk, and companies betting against change are being forced to rethink everything. Tesla has proven that after 100,000 cycles, testing shows the battery performs 13% better than when it was brand new, far above their initial claim of 7%. This opens the door to applications far beyond electric cars, extending into heavy transport, electric aircraft, and even military systems. The real weapon isn't the abundance of aluminum, it's breaking free from the rigged game entirely. China's strength has been built on scarcity. Lithium, cobalt, manganese, all difficult to mine and refine, with complex supply chains. In contrast, aluminum is abundant, inexpensive, and distributed across the globe. And with the new architecture Tesla has developed, it has now become a viable option for something that was once the exclusive domain of lithium. When this news broke, it came as quite a surprise. Since its founding, every battery Tesla has used has contained lithium. In recent years, the company began shifting toward batteries with lower lithium-ion content, such as NCA and NMC, but had never fully eliminated lithium from the equation. Tesla's move to reduce its reliance on lithium isn't all that unexpected, though, given how wildly its price has fluctuated, so much so that even Elon Musk himself has publicly complained about it.
So the price of lithium and all the raw materials and the battery cells went crazy. It doubled. The price of cells doubled. The price of lithium, I think, went up at almost fivefold or 500%. Went up crazy numbers.
That's why batteries still dependent on lithium seem far too expensive for Tesla to truly hit the price point of its upcoming flagship products, most notably the $15,000 affordable electric car and the humanoid Tesla bot, Optimus. The best solution may be to move away from lithium-based batteries altogether and instead use a cheaper, more abundant material, and right now aluminum is the most promising choice. But what exactly is an aluminum-ion battery, and why does it matter so much for affordable EVs? Explaining battery technology can be tricky, especially since most of us aren't chemistry experts. In simple terms, you can think of an aluminum-ion battery as one that uses aluminum as the primary charge carrier instead of lithium, and that's not wrong. But this simple explanation doesn't really help us understand why aluminum is a better choice than lithium, and that's the key point. This isn't just a simple swap of one material for another, it's a complete paradigm shift. It's like trading a horse-drawn carriage for a spaceship. Aluminum ions move through the cell structure 23 times faster than lithium ions, thanks to a new architecture called a quantum tunnel. That alone is a huge leap forward, but it goes even further. This quantum tunnel-based structure isn't just fast, it's smart. Each battery cell contains nanostructured graphene channels capable of self-repair during charging cycles. While traditional lithium batteries degrade with every use, Tesla's aluminum-ion batteries actually become more efficient over time, almost as if they're learning and getting stronger through use. What excites us most about this battery is that it not only has a significantly higher energy density than current lithium batteries, but also lasts 3 times longer. Reports say Tesla's aluminum-ion cells have achieved over 700 watt-hour per kilogram in real-world testing. That's far beyond what most people imagined, because with a 700 watt-hour per kilogram battery in a Tesla or any similar EV, the driving range could easily hit 700 miles, or even 1,000 miles. How is that even possible? Simply put, the current Tesla Model 3 long-range all-wheel drive delivers 346 miles of range with its 79 kilowatt-hour lithium-nickel-manganese cobalt oxide batteries, NMC batteries. It has an energy density of roughly 180 to 200 watt-hour per kilogram. Now compare that to an aluminum-ion battery with 700 watt-hour per kilogram, about 3.5 times higher. Swap the Model 3 all-wheel drive pack for an aluminum-ion pack of the same size, and the range could theoretically jump to around 1,038 miles. However, it's important to note that while aluminum-ion cells can reach 700 watt-hour per kilogram at the cell level, energy density drops slightly at the pack level due to components like casing and cooling systems. With such a high-density battery, shrinking the pack size becomes the key to slashing costs. That's why, instead of over 1,000 miles, a more realistic figure would be around 767 miles of range. And yes, from a basic chemistry standpoint, lithium can't hold a candle to aluminum. In terms of charge density per ion, aluminum is in a league of its own, with each ion carrying 3 times the charge of a lithium ion. In theory, that means aluminum batteries can store far more energy in the same space. A very exciting prospect indeed. Have you ever wondered why EV batteries or the batteries in your electronic devices are so prone to short circuits, sometimes even catching fire or exploding? It's no coincidence that they're almost always lithium-based. What you might not know is that one of the most dangerous issues with lithium batteries is the formation of dendrites. Put simply, dendrites are tiny, needle-like metal crystals that can grow during charging. These sharp structures can pierce the separator between the battery's two electrodes, causing short circuits, fires, explosions, or even total system failure. Dendrites are especially dangerous in lithium metal batteries or under fast charging conditions. They're the reason Tesla and other manufacturers have poured massive resources into control measures, redesigning separators, implementing advanced battery management systems, and more. And all of these efforts only drive the cost of lithium batteries even higher. The moment Tesla's aluminum-ion battery was announced, safety and durability were the first things that came to mind. Based on what we've researched, aluminum ions, when used with certain electrolytes, especially liquid electrolytes similar to those found in lithium batteries, almost never form dendrites. Studies from Stanford and other laboratories have shown that aluminum batteries can endure tens of thousands of charge-discharge cycles without dendrite formation. This is thanks to the far more uniform and stable release of aluminum ions compared to lithium ions. Fires caused by lithium batteries in EVs have always been a major customer concern. As you may know, the smoke released from burning lithium is highly toxic and extremely difficult to extinguish. And despite years of development and improvements, progress in safety has been frustratingly limited. Which Tesla models are using aluminum-ion batteries? Tesla plans to manufacture these batteries entirely in the United States, at a new expanded facility adjacent to Giga, Nevada. The production line is expected to be up and running by the end of this year, once all the equipment is installed and fully calibrated. These new batteries have clearly been under Tesla's radar for quite some time. Although the company has kept details under wraps, internal leaks have made it clear that Tesla wants the public to know they're making a major breakthrough in EV battery technology, especially for the more affordable models set to launch soon. What's remarkable is that this new battery uses materials that are far more common and significantly cheaper than lithium, yet it delivers 3 times the energy density compared to current lithium-ion batteries. Of course, no technology is perfect right out of the gate. There are still a few hurdles to overcome. But overall, this battery outperforms in nearly every aspect. Once those final challenges are addressed, it won't just compete with lithium. It could completely replace it, ending lithium's dominance once and for all. Lithium prices have experienced significant fluctuations over the past 2 years, sometimes dropping, but more often soaring. As Elon Musk has pointed out, lithium prices have surged by as much as 500%. In 2024, the average price of lithium carbonate hovered around $8,000 per ton, and by February this year, it had climbed to $9,271.17 per ton. But that's only part of the story. Beyond lithium, most lithium batteries also require cobalt and nickel, 2 materials that are often even more expensive than lithium itself. This is one of the main reasons why electric vehicle battery costs remain high and why affordable electric cars are still out of reach for many average consumers. Of course, cost is just one piece of the puzzle. Performance is equally crucial. It's no coincidence that lithium batteries have been considered the gold standard for decades. Despite safety concerns, lithium batteries have proven to deliver consistent and reliable performance, which explains why they've maintained dominance for so long. When Elon Musk decides to back a new battery technology, cost is definitely a top priority, but it's clearly not the only factor to consider. Aluminum-ion batteries also have to meet strict performance standards in real-world testing. As mentioned earlier, aluminum-ion batteries benefit from fundamental chemical advantages. Ions of aluminum carry a positive 3 charge, whereas ions of lithium carry only a positive 1 charge. In theory, this means aluminum-ion batteries can store significantly more energy in the same amount of material compared to lithium-ion batteries. The combination of extremely high performance and sustained efficiency throughout the battery's lifespan paints a picture of Tesla not only leading the charge, but also running the race on its own terms. Internally, Tesla engineers describe this new cell as a living organism. It has the ability to adapt, adjust, and respond to the driver's input signals. Microscopic sensors distributed throughout the battery cells monitor temperature, pressure, and current in real time, adjusting graphene channels according to operational stress. This system is not only sophisticated but almost biological in nature. It fundamentally changes what we expect from a car battery. It's no longer just a passive block storing charge. It's an intelligent system that interacts with both the vehicle and the driver. All of this explains why the battery's launch has been so tightly guarded. There have been no flashy announcements or big marketing campaigns, just quiet testing, internal technical reports, and strict security measures. Tesla understands that what they have is sensitive, strategically valuable, and potentially game-changing, both economically and geopolitically. For decades, lithium-ion batteries have been stuck at a theoretical maximum energy density of around 250 watt-hour per kilogram. But Tesla's breakthrough with aluminum-ion batteries shatters that ceiling, reportedly achieving over 600 watt-hour per kilogram in real-world testing. To put this into perspective, the current Tesla Model Y long-range rear-wheel drive offers a range of about 357 miles, using a 75 kilowatt-hour lithium-ion battery pack. If that same pack were replaced with aluminum-ion technology, while keeping the size unchanged, the Model Y could potentially exceed a 1,000-mile range on a single charge. Sounds unbelievable, right? Hitting a 1,000-mile range might seem like an exaggeration, but it's very likely just around the corner. The reason is simple. The higher the energy density of the battery used in an electric vehicle, the lower the overall weight of the battery pack. And with a lighter battery, the car benefits from improved aerodynamics and efficiency. Currently, the production cost of lithium ranges from $55 to $100 per kilowatt-hour, while aluminum manufacturing costs only about $15 to $25 per kilowatt-hour when using standard aluminum processing techniques. The price of aluminum itself is approximately 1/50th that of lithium per unit, and production complexity is significantly reduced thanks to a well-established global infrastructure for aluminum processing. Simply put, a 63 kilowatt-hour battery pack for the Tesla Model 3 currently costs around $6,300 to $6,500, but with aluminum-ion batteries, that cost could drop to approximately $2,000. This single change would dramatically reduce the overall manufacturing cost of an electric vehicle. Simply put, if the current battery pack for the Tesla Model Y costs between $9,300 and $11,400, switching to aluminum-ion batteries could bring that cost down to around $4,300 to $5,300. This change alone would significantly reduce the overall production cost of the Model Y. So, when will aluminum-ion batteries be used in Tesla, Model 2, and Tesla Optimus? The Tesla Model 2 is expected to be manufactured at Gigafactory Texas, Gigafactory Berlin-Brandenburg, and the planned Gigafactory Mexico. Tesla's decision to explore Li-ion batteries for the Model 2 is driven by the need to reduce production costs and improve vehicle performance. Li-ion batteries offer several advantages over traditional lithium-ion batteries, including higher energy density, faster charging times, and lower material costs. These benefits align with Tesla's goal of producing an affordable electric vehicle without compromising on quality or performance. While specific timelines for the integration of Li-ion batteries into the Model 2 have not been disclosed, industry experts anticipate that Tesla will begin incorporating this technology in the coming years. The adoption of Li-ion batteries is expected to coincide with the launch of the Model 2, which is projected to occur in the near future. Tesla's Optimus robot, a humanoid AI-driven assistant, represents the company's foray into robotics. While the primary focus of Optimus is to assist with tasks such as manufacturing and logistics, the integration of Li-ion batteries could enhance the robot's capabilities. The lightweight and high-energy characteristics of Li-ion batteries would allow Optimus to operate more efficiently and for longer periods without the need for frequent recharging. While Tesla has not officially confirmed the use of aluminum-ion batteries in the Model 2 or Optimus, the company's ongoing research and development efforts indicate that this technology could be adopted in the near future. The potential benefits of Li-ion batteries align with Tesla's objectives of reducing costs, improving performance, and advancing innovation in both the automotive and robotics sectors. As Tesla continues to push the boundaries of technology, the integration of Lithium-ion batteries into its products could represent a significant step forward in the evolution of electric vehicles and intelligent robotics. But given that aluminum-ion battery production costs are much lower than lithium-ion, do you believe Tesla will significantly reduce EV prices by adopting this technology? Or are there other barriers keeping prices high? Please share your opinion in the comments section below this video. Thanks for watching our video. Subscribe now so you don't miss the next breaking Tesla update. It's coming in just 2 days. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Also make sure to turn on notifications so you never miss our latest videos. We appreciate your support and look forward to seeing you in the next video. Goodbye.